Well, whatever.
Yeah,
You know what I mean? You got it? Okay.
Good morning. I'm Mark Godin. I'm with PTAC. I'm pleased to welcome you this morning to this webinar by Enhanced Geothermal Energy Solutions and E2E Energy Solutions, sorry, and about enhanced geothermal reservoir recovery. So it's a very exciting geothermal application that has the promise to deliver significant value to green energy and the overall energy sector in Canada. Before I turn it over to our presenters, I want to do a very brief introduction, a safety moment, and for the last year and a half and counting, the reminder is about the current pandemic and an encouragement to everyone to follow public health advisories and local regulations or rules in your jurisdiction, so that as a society we can move away from this situation, as we all wish that happens sooner than later. PTAC is a not-for-profit industry association. We have been in operations for 25 years, and we're proud of our track record over this time period. We have facilitated the introduction into the Canadian energy sector of novel, exciting new technologies, such as the one we'll be talking about today. And we have part of our mandate is to do these webinars, introduction to new technologies, and we host these webinars in the order of 20 per year. And also I mentioned that we have workshops and conferences on a regular basis, and coming up in 2 weeks is our annual methane emissions reduction forum, which is a well-attended, free to attend for PTAC members and CRIN members. Please look on our website for registration. The webinar is being recorded. We will, for the purpose of being able to play it back on demand from our website for your colleagues. If you find it interesting, you can inform your colleagues that it's available for download and viewing at another time if you happen to have a meeting or other engagement at this time. I am pleased to welcome our presenters today, and our first with an introduction to the company. So E2E Energy Solution aspires to design and develop economically viable solutions for a sustainable net zero carbon future through its proprietary enhanced geothermal reservoir recovery system. The company believes that the economic advantages and synergies between the different revenue streams achieved through the process positions E2E to become a global leader in providing economic and sustainable green energy solutions. I will introduce our first presenter, and who is Nick Daproshida. He is President and CEO of E2E Energy Solutions. Nick brings with him over 25 years of entrepreneurial and leadership experience in a variety of sectors. Having strong ties with the Canadian energy sector, Nick was able to recognize the shift away from fossil fuels to green energy, which inspired him to follow his passion in geothermal energy. With his 30 years of electrical and construction expertise, combined with this passion, Nick founded E2E Energy Solutions to provide new solutions for the rapidly changing Canadian energy sector. He will be joined by Dr. Aref Sayed Nayafi, Dr. Sahar Gennady, and Chris Borowski. And I will leave it to Nick to provide further introductions. So Nick, welcome to the webinar, and I will turn over the podium to you.
Thank you, Mark. And thank you, PTAC, for allowing us to present today. Good morning. My name is Domenico Nick DeProcida. I am the president and CEO of E2E Energy Solutions. Today, we'll begin with our video presentation, which provides a broad understanding of E2E's patent-pending EGRS process. After the video, I'll be providing a brief introduction to E2E Energy Solutions, specifically what inspired its creation and the potential opportunity it'll create for the oil and gas industry. Following my introduction, Sahar Gennady from Ashaw Energy will then review the results of the simulations performed on the EGRS process. Followed by Chris Borowski, the designer of our economic model, who will be discussing the financial potential of our technology, and then finishing off with hopefully a very interactive question period. Please enjoy the enhanced geothermal reservoir recovery system video.
E2E Energy Solutions strives to design and develop economical solutions for a sustainable net zero carbon future using its patent-pending process, Enhanced Geothermal Reservoir Recovery System. E2E's EGRRS process targets qualifying producing and non-producing oil and gas reservoirs and converts them into large-scale geothermal power plants capable of generating 50 to 100 megawatts. 2 to 4 wells are selected within 4 kilometers from each other. The wellhead is removed off of the first injection well, and the directional drilling rig is set up. The wellbore is then re-entered and drilled down to and through the reservoir, continuing to a depth that yields temperatures above 200 degrees Celsius. Once the desired depth has been reached, the drilling is then turned and continued to a central location where the recovery well will be located. The drill is then removed and the perforated pipe is installed in the horizontal zone. Once the perforated pipe is installed, the formation is hydraulically fractured. A second conduit is then installed in the wellbore and connected to the first. The portion of the conduit passing through the reservoir is designed to enhance gas liberation from the reservoir brine, which can then be recovered at the wellhead. With the gas removed from the brine, the hot fluid flows down the conduit to the fractured zone to complete the first injection well. The same process is then replicated at the second well and any additional injection wells that may be used. After all the injection wells have been completed, a recovery well is strategically located at a central location and drilled to the same depth as the injection well. Multiple horizontal legs are then drilled from the central recovery well, intersecting the fractured zones of the injection legs. The perforated horizontal recovery conduits are then installed, intersecting the injection legs fract zone. The recovery legs are then fractured, creating a deep earth radiator at temperatures of 200 degrees Celsius or higher. As the hot reservoir brine passes through the gas recovery conduit in the reservoir, the trapped gases are liberated from the reservoir brine, which then travel up the conduit to the wellhead, where they are recovered. The remaining hot brine flows down the injection conduit to the created deep earth radiator. The hot brine then slowly flows through the fractures, where the temperature is upgraded to greater than 200 degrees Celsius and is recovered by the injection legs and brought to the surface. At the surface, the hot brine is passed through a separator, where it flashes into steam. The steam is then used to drive a turbine to generate electricity. The condensed steam and water are then treated and sent to the hydrogen electrolysis process. A concentrated brine is created after the steam is separated from the reservoir brine. This concentrated brine is then treated and sent to the lithium extraction process. The recovered natural gas from each injection well can be sold directly to market or reformed efficiently into hydrogen, utilizing the produced steam and generated electricity to power the SMR plus carbon capture process. The heat recovered from the lithium and electrolysis process, combined with the electricity and clean water produced from the geothermal power plant, can be used to heat and power sustainable greenhouses. The produced green electricity can also be used to power energy-intensive AI and cryptocurrency mining. The remaining water and any carbon produced are treated and re-injected back into the reservoir, away from the production zone. E2E Energy Solutions, with its economics-first approach to renewable energy, creates green energy projects with economics that make sense.
We hope you enjoyed the video and found that it provided a good introduction to our EGRRS process. The inspiration for the enhanced geothermal reservoir recovery system came from the struggles and hurdles faced by our oil and gas sector today, and the need to start moving in a new renewable direction. As you know, some of the major problems faced by industry today are huge investments in infrastructure and land leases, rising costs of carbon impacting the bottom line, future demand for oil and gas dropping, lack of economics of renewable energy projects, bad optics public perception around carbon emitting fuels, and lack of new investment into the oil and gas sector. E2E's enhanced geothermal reservoir recovery system was designed specifically to address these issues that are plaguing our oil and gas sector by providing a vehicle for industry to repurpose their existing sites and infrastructure and to create renewable energy while continuing to produce their oil and gas reserves for as long as the market allows. We were able to identify that geothermal power generation from existing oil and gas reservoirs is possible in some locations, but would not be economically viable without the enhancement to the reservoir. Our process addresses this problem by enhancing the temperature and flow of the reservoir brine, and in turn, greatly increasing the geothermal potential. The second problem with repurposing the existing oil and gas reservoirs is geographical location and the lack of grid access. We were able to overcome this problem by identifying the synergies between our geothermal process and other production of many other high-value energy-intensive commodities that have the potential to remove large energy loads off the energy grid in areas with no grid access. This addition of these high-value commodities increases efficiencies and adds new, valuable, renewable revenue streams to raise overall revenue and cash flow of the project. The EGRRS process also generates valuable carbon offsets and clean fuel credits, which can be used to offset carbon penalties against other carbon-intensive production or be sold directly to market, creating additional revenue and improving the overall economics of the project. Now, please welcome Sahar Gennady from Ashaw Energy. Ashaw Energy was engaged to construct and perform simulations on E2E's EGRRS process. I will now turn the presentation over to Sahar to present the results.
Hello, everyone. Thanks, Nick. I am Sahar Gennady, president of Ashaw Energy. We have a pleasure working with E2E in a modeling site and also evaluation of the feasibility and proof of concept of EGRR process. Firstly, what is EGRRS? EGRRS is Enhanced Geothermal Reservoir Recovery System, which is a hybrid of conventional and enhanced geothermal system. The EGRR process is concept which tries to leverage from the benefit of both methods. One of the main benefits of EGRRS is that it uses the previously heated water from the aquifer. In EGS and closed loop, the injection is from the surface. That water is around 20 degrees Celsius. But in EGRRS process, water is injected to aquifer and then it produced in fracture system. Since it is a fractured well, another advantage is that it is using much larger contact area in comparison to closed loop. Also, since EGRRS repurposing unused and unproductive oil and gas wells, it can help the economics by reducing the cost of redrilling and also abandonment. The pressure decline in aquifer can be maintained by reinjection of the produced fluid. The focus of this modeling is on EGRRS proof of concept. The design and optimization of the geothermal exploitation process requires careful analysis of the transient heat transfer and fluid in porous medium, and also hydraulic modeling of the system. And the design of the pilot and commercialization is relied on numerical modeling. To understand the relationship between water injection and heated water production and its variation in time, many components need to be coupled. To apply the numerical modeling, we should create the structure that handles and couples all the components in one system. The target in EGRRS is to deliver 600 meter cube per hour at 200 degrees Celsius as surface. And to create such a rate and wellhead temperature, typical target reservoirs are numerically modeled to find the best location for pilot. The typical geological parameters and configuration is presented in this figure. Also, many different configurations have been modeled, but this one, which has a 2 kilometers of horizontal section and 2 vertical depth of 7 kilometers. Also, aquifer temperature is 100 degrees Celsius and average porosity of 8% and average permeability of 500 millidarcy considered for this analysis. Although the operation and implementation of EGRRS is quite simple and current technology is available to be used, but the numerical modeling is quite complex and required many new techniques to be implemented. In this figure, we can see the complexity of the EGRRS that should be considered and modeled, which are the interaction between reinjector and producer, and also gravity flow into the hydraulic fracture zone and flow into the producer. The major part of heat interaction is happening in hydraulic fracture zones. As flow moves horizontally, some of the flow moves into the fracture and then move into the producer. To calculate the actual heat transfer, the rate that goes into the well or fracture should be calculated accurately. And then different heat transfer calculation can be modeled for different sections. The heat transfer between fracture has 2 components of conduction and convection inside the fracture zones that should be modeled totally different from the wellbore. One of the main parameters is half-length fracture, which is shown in right-hand side in a picture. In here, the wellhead temperature versus time is compared for different half-length fractures, and we can see the most important component of process is the fracking and should be engineered properly. By increasing the half-length, the temperature decline versus time is decreasing, and we can keep the temperature for longer duration. Even with 100 meters of half-length fracture, we can keep the preferable temperature for about 4 years. But having shorter half-lengths, such as 50 meters, is not enough for power generation. For a single well, the temperature profile is compared here for well with and without hydraulic fracture. In a blue line, we can see without hydraulic fracture, and red line shows with hydraulic fracture. And we can see how fracturing improves the heat transfer. In geothermal system, the surface facility, including turbine, is designed for a small window. One challenge is that what if the hydraulic fracture half-length did not go as long as it is anticipated and temperature decline faster? Since heating interaction with geothermal reservoir is controlled with conduction and the surrounding temperature took some time to recover. Therefore, to extend the life of EGRRS, flow can be alternate between legs to improve lifespan. In EGRRS, we should combine the output of different wells to provide the maximum efficiency, and this design should be engineered properly. The wellhead temperature on each production well is shown in a chart that temperature versus 2 years. And we can see that temperature dropping with time, and we should operate it in sequence to keep the temperature in design window. You can see how the combined temperature fluctuation is less, and with having more wells, the fluctuation can also be reduced. It must be noted that still we required new wells as we develop the project, and drilling and fracking is expected to be part of the maintenance strategy. The electrical power is one of the major output of EGRRS. The enthalpy method is used for initial evaluation of geothermal power output by the binary unit at surface. The variation of power with rate is plotted in here. For one leg, it is expected to have 10.4 megawatts. Based on the simulation conducted, we concluded that to improve the required outlet fluid temperature, we should increase the surface area, and minimum 100 meters of half length initially would provide a temperature over 200 degrees Celsius for a period of approximately 4 years. And also, we have seen that with EGRR process, we are able to generate the desired temperature and flow rate. Geothermal energy is not a new concept, but due to current need, there are different applications developing every day. The complexity of such a model cannot be captured with old applications, and there is a need for new softwares. Ash energy that is previously known for dynamic modeling of conventional and thermal application with complex completion is now focused on providing a full package of geothermal from closed loop, EGS, and more complex ones such as EGRRS. The neat part of the packaging is that it is designed for operational concept and also keep all the historic data in one application. Now I want to take a chance to introduce Chris Brovsky, and he want to talk about the financial analysis of EGRRS process. All yours, Chris.
Thank you, Sarah. Right, hello, everyone. I will be using the next few slides to walk through some economic potential of a process that we developed. So for the purposes of this presentation, we have developed a virtual reservoir that we wanted to speak to. Each reservoir in practice will have unique characteristics in terms of its productive potential and its scope. Production assumptions and economic assumptions that we've utilized for these purposes are as follows. We've assumed a 50 megawatt facility, that lithium, hydrogen, and natural gas will be sold. Water and natural gas that are required for the process are sourced from the reservoir and sufficient to sustain operations, while any excess electricity or natural gas will be sold to market. It's important to note that any carbon offsets and clean fuel credits that would be to the benefit of E2E and the financial feasibility of a project have been excluded. Those will be included after we complete detailed analysis. In this example, we have assumed that each process will utilize a third of the electricity generated. In practice, the products produced will be based on the specific characteristics of the reservoir and optimized for profitability. The amounts shown over the next few slides are in Canadian dollars unless otherwise noted. For the capital expenditures, the total that we've assumed here is about $600 million. The total Please note that this capital intensity is higher than expected as these amounts are not optimized. Again, in practice, the capital expenditures would be optimized based on the characteristics of the reservoir and to maximize profitability. The commodity price assumptions that we have used are shown below. For the lithium, it's $20,000 per ton of lithium hydroxide, $2 per kilogram for hydrogen, $4 per gigajoule for natural gas. And in our model, we've assumed annual increases of 3% a year. The system in this sample reservoir or project has been designed to produce 2,700 tons a year of lithium hydroxide, 15.2 million kilograms of blue hydrogen a year, and 2.4 million kilograms of green hydrogen per year. The next few slides summarize the output of the financial model. A few important assumptions that we have used are as follows. On the lithium production, we have assumed a reservoir concentration of 75 parts per million, with 90% being recoverable. For the natural gas production, we've assumed there's production from 3 wells, which decline at 10% a year. And the blue and green hydrogen that are produced from those volumes produced are based on current technology. The financial results, more specifically the operating profit, are summarized on this slide. I won't walk through all the numbers here, but the main numbers I'd want to point you to are at the bottom of the slide, which show the average annual operating profit of about $100 million a year. This slide summarizes the free cash flow summary. The free cash flow is comprised of the capital expenditures that are required to produce and to design the project, and the free cash flow that's generated over time. In this sample scenario, our initial capital expenditures are about $600 million, with a total capital expenditures over the life of the project of $740 million, with a project life of 20 years. Over the life of this project, the illustrative operating profit was $2.3 billion, the total capex of $740 million, and a pre-tax cash flow of $1.6 billion. In summary, based on this sample reservoir, the sample project, and the scale, that the payback period on this project would be 6 years, provide a internal rate of return of 5.4%, and a net present value of $170 million. A couple of important points to note on the economic results are that it does not include the carbon offsets or clean fuel credits. Also, it's independent of any financial or any financing structure that would be in place, for example, any bank debt or any agreements with partners. That's the conclusion of this economic summary section, and I'll turn it back to Nick.
Thank you, Sahir and Chris. The EGRS process is a combination of many real-world technologies that are still in use today around the world and have been for many decades in a variety of sectors. Many of the same processes used by our oil and gas industry apply to geothermal, for example, drilling, hydraulic fracturing, geology, and engineering. It is E2E's plan to create many new job opportunities for the energy sector by repurposing existing infrastructure and expertise from the oil and gas industry. The Ashon model clearly shows that the EGRS process works to easily achieve its aggressive temperature and flow targets, significantly reducing the risk of a pilot. As mentioned previously, our technology was developed using technology and processes that are commonly used today, which have been modified to work with our enhanced geothermal reservoir recovery system. I would now like to wrap up the presentation portion of our TIS with the reasons we're here today. E2E is actively looking to secure a qualifying site and industry partners interested in participating in the design, funding, engineering, and construction of our pilot project. A qualifying reservoir for E2E's process would need to have high porosity and a minimum gradient of 35 degrees Celsius per kilometer to be considered. This now concludes the presentation portion of our TIS, and we'd once again like to thank PTAC and all those who took the time to be with us here today. We now look forward to your questions.
So thank you, Nick, and your team. And I'm glad that is an exciting presentation and some very impressive numbers and potential here for green energy in a profitable way. I will so I invite the audience here to ask their questions in the question panel of the platform. And I see we already have two questions, and I will, now three, so awesome. Keep them coming. So I will read them one at a time and offer the team the opportunity to provide a complete answer to those questions. So the first one is, what is the vertical depth of wells that need to be drilled?
Sorry, 1 second. We're just having some technical difficulties. Our apologies. We lost sound. Can you say something? There we
Did you hear
go.
my question?
Sorry, no.
No,
Now continue the question.
So I will repeat it, no problem. So that's a question coming from the audience, the question in the question panel that I invite the audience to utilize to pose their questions. So the first question is, what is the vertical depth of the wells that need to be drilled?
The vertical depth is, in our model, we've shown it at 7 kilometers. The TVD of our reservoir was 2 kilometers. So we're going down an additional 5 kilometers and then horizontally for 2. But these depths will be dependent on the gradient that exists on the reservoir. The higher the gradient, we wouldn't need to go as deep for a higher gradient. We're shallower at lower gradients.
Awesome. So should I summarize it as 2,000 meter down and 5,000 meters horizontal?
No, it would, the bottom of your reservoir would be between 2 and 3 kilometers, 2 or 3,000 meters down. And we would be going down an additional 2,000 to 3,000 meters to achieve the temperatures that we're looking for. So if the gradient is a higher gradient, we wouldn't need to go as deep. With a lower gradient, we'd have to go deeper.
Perfect. And I also invite the people in the audience, if you want to make this as interactive as possible. So if you have follow-on questions, please put them in the question and answer panel. I'll move on to the next one. How far have you gone into physical R&D activities to validate the modeling?
As far as physical activities, that's what we're looking to do next. And we need a reservoir, we need a site to start working on those physical activities, to analyze the reservoir and everything, all the properties around it. So that's our ask. Is that
Yes, and as you said,
partners to work towards.
Yeah, as you said, Nick, it's all the components of technologies
They exist. Yeah,
exists, right? So
Yeah.
there's no point in retesting those, right? So
exactly.
so the next step in the development of this technology is a pilot, as you said.
That's correct.
The next question, what would be the impact on the financial analysis in using a 5 megawatt plant?
I think the economic impact would be significant, as E2E is mainly focused on larger facilities and targeting just larger scale production. With the smaller facility, the capital intensity is likely to be much higher, likely to reduce the profitability, and which would very likely result in additional carbon offsets, any grants, and any government support that's likely to be as profitable as a large scale opportunity. Maybe on the smaller side, a project could be quite profitable, but it's likely that profit would come from natural gas sales as opposed to the full system that we've presented.
And just to expand on that a little bit, E2E would be looking to enhance a reservoir that only had the ability to produce 5 megawatts. That's the design of our process. So if our reservoir can produce 5 megawatts, and there is reservoirs in Western Canada that have that ability, we're looking to expand on that and enhance the reservoir's ability to bring it up to 30, 40, and 50 megawatts.
Very good. And 50 megawatts is an awesome number. So I think definitely the energy demand for green power is in that scale. But I'll ask well, I guess my takeaway from your answer is that you are at E2E Energy Solution are willing to, 5 megawatt is not out of the question, and it's something you're willing to discuss with a potential opportunity. And
Definitely,
it depends
yeah.
on a number of factors, right? So, and I'll ask just one more question here related to this. It's not in the question panel, but do you have a sense of what uptick on your financial performance comes with adding the carbon offsets to the revenues?
Well, that's something we've been diving into, and we've been hesitant to use any, simple rules of thumb or anything like that, as we believe it could be significant. And it's just as the pilot project is a next step, so is that analysis.
Okay, very good. So it kind of says that a 5 megawatt, even though you lose the economies of scale, if you add carbon offset, you might have something that's viable, not as great as 50 megawatts, but still doable.
Correct. Yep.
Okay. Next question here. Thank you for the presentation. Do you have an example of a reservoir in Canada similar to the one that's used for the simulation model?
We do. I don't know if we should be disclosing it.
That's fine. You don't have to disclose it, but
Yeah,
first answer,
we do have a
it,
couple
right?
sites that we've been looking at quite closely. One's in Alberta and one's in British Columbia.
So this is not an aspirational or fantasy reservoir. It's
No. We've been looking at real reservoirs. Well, we've been doing this, identifying some really good targets.
Perfect. Okay, next question. First comment is very clever technology. So thank you for this comment.
Thank you.
And the question is, what is the levelized cost of power?
The cost of production?
Well, the cost of power in cents per kilowatts. Like what would you see as the sale price of this energy? And I guess as I think of your presentation, that may or may not be not easy to answer because you're not selling power fundamentally. You're doing a lot of value added on-site production with the power. So
yes, selling power to the grid is always an option. It isn't our focus. We've focused on the oil and gas industry and more remote locations where they struggle with no grid access. That's what our concept was built around. But saying that, producing a geothermal power plant does have the option to sell to the grid. I don't have the answers to your question, but if you would like to reach out to us after, we'll definitely find the answers for you and we'll answer them.
Perfect. Next question. What is the main takeaway for the audience? What is the core ask from today's presentation?
The core ask from today's presentation is we are actively looking for partners for a site, number one, that we can propose for our pilot project, as well as partners that are going to work with us on the engineering, the design, construction of our pilot.
Perfect. That's very clear. So next question. Most reservoirs in Northeast BC and Northwestern Alberta are extremely sour. How will you deal with that? Do your models account for that?
Yeah, the model we consider some sort of corrosion, but because it's the seal is a typical reservoir and we don't have exact numbers, we don't really go based on the actual results, but we put some values on the salinity, alkalinity of the water, because really like the sour thing is going to dissolve in the water and that water pass through the fracture And it depends if it's a carbonate reservoir or it's a fully granite. Those parts is geochemistry of that part is a bit difficult if you don't know all the components. But we assume some sort of corrosion, especially the pitting corrosion we added. But the typical aquifer water, not having another H2S coming into the water, would be the solubility. If that's the case, we may want to go and inject the gas back into the system in the aquifer further on that we don't see the interaction. But for now on, in the modeling, we don't have any H2S added, but we add a lot of alkalinity and like in the concept of the what's the water spectrum is. And we consider only corrosion, but we only consider the pitting corrosion, not the general corrosion in this model.
Perfect. So it is something you've thought about and have strategies to deal with. Next question is, what technology are you looking at for lithium extraction?
The technology we're looking at right now is the electrolysis technology. That's a rapidly changing space, the lithium extraction from brine, and it's pretty early on. So we are talking with third-party groups. We haven't really hung our hat on one specific process yet, because you see as we go through this, that's going to be more in the end stages, and it's not incorporated in our pilot. Our pilot is going to be strictly the geothermal. So as we progress through, we will work with the most current technology and third parties that are in the market that are available.
Yeah, perfect. And prior conversation we've had, that also presents an opportunity for these third parties to become partners in the project, if you will, right?
Correct.
Yeah. And the next question, and actually the last one we have on our question panel, and hopefully it's not the last, invite the audience to ask more. It sounds like you need a very specific reservoir to do this. How do you get the lithium and the hydrogen to market to actually get the prices that you mentioned? The prices seem very high for being in perhaps a remote location.
Actually, I just want to clear something up right now. On the surface, what we've provided are examples of what they may not be included in every facility that we built. It's going to be reservoir dependent. If we have favorable concentration or lithium concentrations, we'll definitely harvest them and get them to market if the economics make sense. If they don't, there are other revenue streams that we can access, such as AI, cryptocurrency mining. There's green hydrogen, lithium. There's always options to sell to the grid where available. So I don't want everybody to view this as this is the model and it's going to be this on every single site. We'll build and design each project to each reservoir and what the reservoirs have to offer.
Yeah, so it is a platform technology, if you will, and the example that was presented in the economic analysis with so many production rates for hydrogen and lithium are, as you say, Nick, just example, and they can go up and down depending on the situation.
Exactly. Our process builds the engine to drive all the other processes. We're generating the electricity, and we're operating that from being able to generate 2 to 3, 4 megawatts up to 40, 50 megawatts.
Yes, and you have the modeling skills, of course, amply demonstrated here to find the optimum profitability for each reservoir.
That's correct, yeah. The surface is to bring the economics.
Yeah. Awesome. So I don't see additional questions here. Maybe because it's a big financial item, if you have the ability to discuss a little bit more. I realize that you already said this may be early, but the carbon offset revenue stream, if you can discuss this a little bit more, because it definitely makes a big difference to the economics.
Yeah, do you want us to go a little bit to that, Chris?
I'm not asking for numbers here, but just tell us what you're thinking and what are the avenues and so.
We viewed the carbon offsets and clean fuel credits as a major contributor to the economics, especially in the early stages we're already on, to help pay down the project and pay the capex. But to accurately give you numbers and to analyze it, we need to have a location, and we need to build out the project and see exactly what fuels we're going to be generating to accurately calculate the clean fuel credits and carbon offsets. So it's an exercise we try to look at doing leading up to our presentation, and it's going to be very difficult until we can actually have a reservoir and determine exactly what we're producing and how much of it we're producing to apply those.
Very good. Another theme here to touch on, and that where you could elaborate, is net zero, and you can use that term, and just elaborate on that, please, about what is the net carbon footprint of the whole site, right? So how do you just maybe reiterate or provide a tidy conclusion on that?
Yeah, and so trying to achieve net zero, and again, depending on what we're producing and doing on the surface. But for products like green hydrogen, there's no emissions, no carbon emissions. SMR, we do have carbon emitted, but our model captures the carbon and reinjects any carbon back into the reservoir. So everything is treated and reinjected.
So there is a carbon capture component if needed into the platform.
It's incorporated with the geothermal. As we're reinjecting the brine, we're going to utilize that process.
Awesome.
The carbon with it.
Awesome. So the location for a site, maybe we can have a little bit of an elaboration on this. So you looked at sites in the Northwest Alberta and Northeast BC. Is that the type of location that seemed to be optimal from your research?
Those are definitely the best sites that we found so far. So a natural gas reservoir is ideal. We can work with any reservoir with enough porosity and gradient. So it'll just limit on what we can produce. So a reservoir would be limited with the natural gas production, but we can still produce the electricity and commodities on the surface. But you're correct in saying, yeah, northeastern BC and northwestern Alberta are definitely our targets.
And how so the remoteness of the site, as I heard the conversation here, is not a key factor, right? You don't need to be close to, I mean, it's nice, of course, but you don't need to be close to pipelines or transmission lines.
No, exactly. And being close to pipelines, depending on where we're going to go with transportation of hydrogen in the future, there's a lot of options being tossed around by industry right now. But the pipelines will have access if we're on oil and gas site. As far as the grid, there's a lot of sites don't have grid access, and that was the inspiration behind our design, to bring economics to these. So we're trying to remove energy intensive loads off of existing grids to these remote locations where we can produce large amounts of electricity and take the pressure off the grid. If we have grid access, we have the option of selling it to the grid.
Perfect. And what maybe you have some comment on the importance of, or lack of importance of, existing wells, like already wells in, how many wells, or that need legacy wells or suspended or active wells, given that you're re-entering, how important to have existing wells?
The importance is more for the economics, because we're trying to repurpose existing infrastructure and save on capex. If we have natural gas in the reservoir and the wells are tied in already, it is a bonus. We can just re-enter the well, build up our plant, and then continue to recover natural gas. So
So ideally,
more
it's,
on an economic,
you're looking for ideally wells at the end of their life, or suspended or about to be suspended.
yes, ideally, we'd like to repurpose those, but we can repurpose any well and then continue production.
Okay, perfect.
The ones that are suspended, we can't liberate gas, so get them to produce again.
Okay. All right. I don't see any more questions here, and I think we've touched on most of the high points. I maybe one last point that may be worth emphasizing here is how a key aspect of your technology, how it differentiates itself from other geothermal opportunities out there, is the utilization of existing or brines in an existing reservoir on site. Maybe you could elaborate a bit on that, how that provides a competitive advantage and enhances the economics.
Yeah, the competitive advantage, we're starting with a preheated brine. We're not taking a brine at 20 degrees Celsius from the surface and trying to upgrade it to 200 degrees. We're starting with a brine 80, 100, 120 degrees Celsius, which enables us to upgrade it to 200 degrees. If we were to take that same brine from the surface at 20 degrees Celsius, the residence time would be dramatically longer, which would impact our flow and the overall ability for us to generate electricity.
Awesome.
So our key is the preheated brine.
Yes, I think that needs to be made clear, repeated, if you will. I know
Yeah,
you said it
that's
before.
what sets us apart from the other.
Yes. So let's proceed to come to the end. So on my side, on the PTAC, I'll just add a few words here that we are open here on PTAC to help out any facilitation on finding a site. So companies or audience, people in the audience have an interest in engaging in those conversations, you're welcome to contact Nick and his colleagues directly, or also us at PTAC, and we will pass on the communication to E2E Energy Solutions. So any channel will work as good as the other. So you can contact us on email or social media. We will have the video available that you watched this morning, available for additional download on the PTAC website. And we encourage you to contact E2E Solutions for engaging in further conversations. So with that, I will pass it back to Nick and his colleagues for closing comments, and then we will end the webinar.
Thank you, Mark. As Mark mentioned, we would love to hear from any producer that feels they have a qualifying site, and they can reach out to us directly. If you do feel you have a qualifying site, like we mentioned earlier, we're looking for a minimum of 35 degrees Celsius with high porosity. And from there, we can do a complete evaluation and qualification of your reservoir. We can take that further into a full economic model that'll show all our revenue streams, potential revenue streams that the reservoir has to offer, as well as any carbon offsets and potential credits that can be earned. So we can do a full economic snapshot of what a project would look like on the reservoir. And with that, we'd like to thank everybody for their time and coming out to view our presentation.
And well, thank you, Nick, and your colleagues. Exciting stuff. And I really hope we can make that a reality, because it is a source of net zero energy and helps all this Western Canadian energy sector to improve ESG goals and meet the needs of the world for climate change. So with these final words, the webinar ends, and thank you for attending.
Thank you.